Hi, in this lecture we are going to discuss about coupling and encapsulation. The goals of this lecture is to think about coupling and how coupling affects different entities in our system. We are going to present the Law of Demeter, which is one of the principles that can guide your design. We are going to discuss about the move behavior closer to data pattern. It's a reengineering pattern from the Reengineering Pattern book. And we are going to discuss about some of the trade-offs of this Law of Demeter, which can have benefits and some drawbacks. Now, have you ever found yourself in one of these situations? Telling yourself, I cannot reuse this component in this other application. No, because it is blah, 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 blah. Or, I cannot easily substitute this part of the system with another one, even if it does similar stuff. Or, look, when something happens in this part of the system, I get impacted here. So, or finally, no, this part I cannot test. No, it's too complicated. So, actually, most of these things, or all of them, are symptoms of a coupling problem. So there is a coupling in some way in the system, and that is so strong that is preventing us evolving our system in some way, either by reusing, substituting, changing, or even test our system. So to illustrate this problem, we have this example here, where actually we have to read it from right to left. So here we have some class here that defines this do method, which is the most important thing right now in our example. And it has a reference to a dependent object. And this dependent object has a reference to another indirect dependent object. So we have a chain of objects. And then this indirect dependent has a method do something. Finally, what happens in the do method is that the source is telling the dependent to give it the indirect dependent and to do the do something. So actually the source is actually taking the dependent, asking the indirect dependent, and talking directly to the indirect dependent. So if you know what is feature envy, the feature envy code smell, this is related to that. I invite you to look up that online. Now, what happens if we want to change some part of this application? Changes are natural, so it's common that we are going to change stuff. So the question is, when we want to change something, how are we going to be impacted? Yeah. So in particular here, if we want to change something here in the indirect dependent, what are the possible impacts that we're going to get in the rest of the system? In this particular case, what we're going to get is what we call waves or chains of effects or changes. So here, what happens is that every time that we change something, that is going to impact the direct users, but also if we don't control it, it can make waves on other more indirect users. So here in this case, if we want to, for example, remove this do something method, we have to go and change this do method because it is calling it. So all these chain reactions or waves, they are evil. They are actually created when we have leaks. So there is a reference to an object that is flowing from some place to another place it should not flow. So we have an indirect reference where it should not. So what we say is that we are violating encapsulation. So one of the key aspects of objects and object orientation is that an object will encapsulate and it will hide its implementation. So if we are leaking the reference of an object to another object, we are giving the other object some pointer to our own implementation. So the question is, how can we limit this leaking? One of the answers to this problem is to use the Law of Demeter. The Law of Demeter is just a principle, a design principle that will give us some guidance in how we can avoid that. So the Law of Demeter says that we can only send messages to arguments, instance variables, an object that we are creating, self, super, and our own class. And that we should avoid global variables and objects returned from messages in general, other than send to self. So how does it work in a real example? So here, for example, this is a method that shows different examples of things that we can do. So if we have a method and we put ourselves in the skin of the object in the receiver, so we have a parameter, so we can send the message self-foo because the receiver is self, so we can send the message to ourselves. Why is that? Because if we change, we only have to change ourselves, so that's okay. Here, we have a message sent to super, so that means that this, if you remember the super lecture, will restart the method lookup from the super class of this method, of the class where this method is. So if this method is in A and it has a super class B, it's going to restart the lookup in B. So again, here we have somehow some dependency to a superclass. If the superclass changes, we are going to get impacted, but we are still in the same hierarchy. So still, this is a controllable change. Now, here we are sending a message self to get the current class, and that, of course, should get us the current class, the class of the current object, and we are sending a message to our own class, so that's okay, and that is allowed by the Law of Demeter. We can also send messages to instance variables, so to object references by instance variables. Here we are sending a message to isVar1 that is referenced to some object, and we also allow messages sent to instance variable accessed by a getter method. So here, this is the equivalent of a getter method that returns the value of isVar1. We can also send a message to parameters, and then we can instantiate objects, and since we just instantiated it, we can actually send it a message. So what this law will enforce is that we are not going to be able to send messages to far away objects. So we don't have to skip intermediate objects. So our source object knows this dependence, and the dependence will know the intermediate dependence, the indirect dependence. So what the Law of Demeter tries to do is to avoid that this guy here sends a message here. So this is forbidden, and this is forbidden too. Like that, if we avoid these faraway messages, we are going to avoid dependencies, and we are going to avoid a chain of changes if we change here. What the Law of Demeter will actually force us to do is that the source here will only be able to send messages here and here, so its action will be constrained to this part of the system. So that means that here we are constraining the changes we are going to do. If we change the dependent here, that is probably going to affect the source, but it's not going to affect anything else in the system. In the same way, we are going to constrain the messages to indirect dependent to the dependent, and like that, if something changes in here, it should only affect the dependent here, and not the source. This Law of Demeter, of course, can be applied in a systematic way following, for example, here, the design pattern that is called move behavior close to data, which has as objective to move the behavior that is being applied to objects close to where those objects are. The idea is to strengthen the encapsulation, so to actually refactor step by step the code that we saw at the beginning and make it closer to what we saw later. So here, for example, if you see this example like this, here we are in the original code where we have a car that is using an engine, and the engine is using a carburetor, and then the engine wants to increase the speed, and to increase the speed, it is taking the carburetor and then changing a flag that is here far away to true. So step by step, if we wanted to fix that in a refactoring, we would first move this behavior to the engine, and like that the car should, since the car should only talk to the engine, we are going to transform this whole expression to engine speed up. So we are going to add behavior, move behavior close to the data here, and like that we move the inner expression in to here. Like that, now in this first step, the car doesn't depend anymore on the carburetor. Now the car only depends on the engine. But now The problem, we just push the problem to the engine. The engine now depends on the carburetor that is actually really coupled with the implementation of the carburetor. If we decide tomorrow to change the implementation of the carburetor and make that flag, instead of a flag, an integer, that will impact also the engine. So we can also apply this in a second step and to hide those details by moving this behavior to the carburetor. So now in the final refactoring, what happens is that the engine will tell the carburetor to open the fuel valve, and then the carburetor can do whatever it wants in its implementation. In this case, it will only set the boolean as true, the flag as true. In this final version, what happens is that the car only has a dependency to the engine, and the engine has a slight dependency to the API of the carburetor. All these dependencies are actually based not on implementations, but on APIs. So they will force that our engine depends on the message open fuel valve, and the car depends on the message speed up, and so on. For another real case, so here we have an example taken from Faro, from the Morphic UI framework, which is actually managing the resolution change. So every time that we change the resolution of the Faro window, this is the code that was being executed before. So this was fixed in the meantime, but it was a good example for the slides. So what happened here is that we had this morphic world that represents the window. And when we were resizing the window, we were actually taking the state of the world, taking the render of the world from the world state, and taking the actual window from the renderer, asking it the backend window, with, which actually represents the physical window from the operating system, asking it its renderer, and finally destroying it. So this is actually not satisfying the law of Demeter. So the same thing happened actually in the lines below, all up to the end. So what actually happens here is that if any of these method changes or any of these implementation changes here in this chain of methods, then this method will be broken too. The solution of this is, of course, to follow the law of Demeter to some degree, to refactor step by step, and to delegate only to the object that we know directly. So here, for example, what happens is that this is the original code that was refactored. Now, every time that we visit the resolution change event, we are taking the world state. So here we are not 100% following the law of Demeter, but we are actually cutting many steps. And we are telling it to update to the new resolution. This update new resolution will do the main 3 steps that we were doing before, but it was kind of hidden in implementation detail because it was difficult to read. So it is doing a full repaint, followed by an update to resolution and checking the screen size. And this update new resolution is executing the destroy, validate, and update tool that we saw before. One of the funny things, one of the important things of this example is that now we can easily change the renderer to implement a null object. For example, here a null world renderer that can implement an empty update to new resolution. So now that we are not coupled to the implementations, we can change part of the implementations, but other kind of implementation. So finally, what you see is that the big method was kind of refactored to a simple method in the right place, doing the right 3 things in a more readable way. Now, it's important to understand that law of Demeter, as I said, is heuristic, or is just a principle. So you should not follow it blindly. So if you just do it too strictly, actually this can lead to problems like a bloated class API. So it can actually create byte APIs for your clients. For example, I will show you later that encapsulating collections can produce large interfaces that are complex to follow and to maintain. So it is important to understand what is reasonable to leak, when it is important to apply the law of Demeter, and when it is important to break it too. So here, for example, in this case, what we have is a method, a class that will wrap a collection that is called senders. And in this case, somebody decided to expose all the collection API in this class. So here, that means that then we have the method do that will expose the do method of the sender, and the method collect that will expose collect, and so on for all the other methods on collections. So that means that the bigger the API of collections, the bigger the API that needs to be exposed by this object. So in this sense, maybe hiding the actual collection was not the right decision in this case. And maybe it would have been easier to just expose the collection to the user. As a conclusion, think about the impacts of changes, think about the dependencies, and think about what happens when you chain messages and chain accesses to variables, moreover. Remember that the law of Demeter is a heuristic, so it doesn't work in all cases. You must use it whenever it actually pays off. So it has benefits, but it can also have drawbacks if it is used wrongly. And think about the move behavior close to data reengineering pattern, which is a good way to move from a bad design to the good design using the law of Demeter.